Okay, hello and welcome everybody. My name is Ax, I'm a Java champion, and it is with my greatest pleasure that I introduce Ondro, also a Java champion, who's going to talk about. I'll let him do the introduction. Ondro, have fun, the stage is yours.
Okay, thank you, Ax, for introducing me to this session. I'm Ondro Mihari, and I will be talking about Java cold starts and serverless, and how fast actually Java can start compared to what I think is a general notion of how slow Java fast or rather slow it is. So a few words about me. Uh, yeah, I'm a Java champion as well as Alex and many others in this conference. I'm also a Czech Java lead. I'm leading the Czech Java user group in Prague, basically, and also coordinating other activities of Java groups in Czech Republic. And I'm also contributing and committing on the specifications in Jakarta EE, a few of them, I think 3 or 4, I don't remember exactly. And I'm a director at Omnifish, a company that I co-founded last year. So let's dive into the session. I'm starting with AWS Lambda life cycle before I introduce Java, because that's what matters, basically, when we talk about Java cold starts. We all know that Java is not that fast when we use it on our local machine, because we use it with application servers, frameworks, a lot of stuff. We basically use Java applications, or a lot of us use it with big applications that just start once um, and keep running for at least a few hours or days. Sometimes it's a critical application that needs to run all the time unless we need to update it. But when it goes to AWS Lambda, it really matters how fast Java or any application that is running on AWS Lambda, how fast it starts. And why? That I'll try to explain. So what is AWS Lambda? AWS Lambda is a service that allows us to start an application, process requests using the application, and then shut down our application. Uh, why we would do that? We would do that because we want to save money, basically, by not paying for the application in the clouds when it's running, but doesn't really uh, process requests. So it's when our application doesn't need to work, we don't want to pay for resources allocated to that application. And if a service, a cloud service, just starts our application, serves a request and stops our application, we can just pay for the time we need to process the request. On the other side, when there are too many requests coming in parallel to our application, AWS Lambda can launch multiple instances, a lot of them, to process incoming parallel requests. So we also don't need to um, consider how many resources we need to allocate before handling these requests. Lambda just starts new instances of our application depending on how many requests are incoming. So at that time, we pay more because if we pay for each instance running and processing requests, but we don't have to pay before, only when there are a lot of requests. So it also pays off when we have peaks in usage, in load of our application. For example, during the day when we process a lot of requests, or during some certain period of time, some events, when we need to recompute a lot of data due to some changes that happen once a day, for example, or even once a month. And then during night or other off-peak hours, we don't have to pay, or we pay much less because we only need a few instances running because we have only a few parallel requests incoming. How Lambda works? It has 3 stages, basically. They also can be separated into multiple stages themselves. But the three basic stages are init, initialization phase, that happens before our application is started or is before it is ready to process requests. And this is called, often referred to as a cold start. I will explain why in a minute. Then a request is being processed. That's during the invocation phase. That's basically our code, our application running, processing requests. This is our code that we wrote, and that uses the CPU on our behalf. And we pay only for that CPU and memory use during this phase. And then at the end, there is a shutdown phase, which basically deallocates the resources and shuts down everything so that we don't have to pay for allocating for these resources being allocated. There are also some optimizations uh, because the shutdown phase doesn't need to happen all the time. And in fact, Lambda optimizes it so that when our application is running and another request is coming, it doesn't shut it down and initialize it again. It reuses the same application instance. That's why a lot of time our application doesn't need to cold start it because it's already running, and it doesn't need to go through the shutdown process. When you have constant flow of requests coming, for example, 1,000 requests per minute, then you most probably need just 10 or 20 instances handling all the requests. And if the number of instances doesn't change, there is a high chance that all of them will be warm. They won't shut down, but they will be immediately reused. And we only basically are in the invocation phase. What we can adjust here is, as I said, the request phase where only our code is executed. Basically, the code we actually care about. That is the code that actually runs, processes a request. In the initialization phase, we can also add some code that sets up our environment, our applications, read some configuration, connects to from database, initializes our frameworks, basically everything to be ready to process the first request. The catch is that this code has to finish in, I think, 2 or 3 seconds. It doesn't have to, it can't last long. And why is that? It's because we don't have to pay for this normally. If we use AWS supported runtimes, we only pay when we actually process the request. We pay for the time and resources. We can allocate more resources, more CPU and memory, and that multiplies by the time. So we sometimes pay more, sometimes pay less, even if we spend the same time in this period, in this phase. But it also sometimes happens that when we allocate more resources, our computation is faster and it doesn't take so much time to finish. So in the end, it's a ratio of resources and time. And sometimes when we add more resources, we have so much less time that we pay less in the end. So it's not always we should choose the cheapest resource, because then we pay for the time we use it, and it may be more. And in the initialization phase, we can put some code that is executed up to those 2 or 3 seconds, which we don't pay for. If we run the request for a minute or so, it's not a big difference. But if the request is 2 or 3 seconds, and we can use another 2 seconds in the functional initialization stage, we should move the code to the initialization if it's really the initialization. For example, if we have some framework or some configuration and that doesn't change between requests, it's better to move it into initialization phase. First, we don't pay for it. Second, is not executed for every request, which would make every request processing longer. So if we can move any repetitive code that happens for every request into the initialization phase, we only pay for the actual code that needs to run to process the request. And together with our code in the initialization phase that sets up our application, Lambda also needs to create the whole environment. So it goes through an extension stage, which is basically it connects all other services we want to use from the AWS ecosystem. It connects them to the environment so that we can use them from our Lambda. It initializes the runtime, so it creates something like a Docker container or some other containers, some operating system, and sets up the basic platform, which in case of Java is the JDK. And then it runs our application. The catch with this approach is basically that in case of Java, this only works or exactly like this with Java 11 or Java 8. If you need a newer Java version, you have a bit different scenario. Then we have to use a custom runtime where we can install any Java version. It doesn't have to be Java 17, it can be 18, 14, whatever. Even with 11, we can basically install anything there. And then we deploy our application to this environment, and all the rest works in the same way. But then it becomes a custom runtime. It's not one of the prepared AWS runtimes. And the rules here is that we now need to also pay for the whole initialization phase, which is not that slow. But in that case, there's no guarantee. We can basically use more time in that phase because we have full control of, or more control of the environment. We can do a lot of initialization there. Besides Java code, we can add some scripts in there, something outside of Java, and then AWS decided we have to pay not even for our code, but also for the AWS code that sets up all the environments. So the rules are either we pay for the whole init phase or we don't pay for it, and we have some computation power for free. But for that we would have to use built-in runtimes, and with newer than Java 11 runtimes, we still need to wait until AWS implements support for Java 17 or newer Java, so that we can use one of the pre-built runtimes with Java 17. So now let's do some comparison. This is a comparison made by somebody who is even more experienced in serverless, and especially in AWS Lambda. And he did a lot of measurements, comparing a lot of different languages, different runtimes. And it turned out that Java is not slower than most of the other runtimes. So it's not the Java language, and not even the implementation, how AWS Lambda initializes Java compared to the other languages. It's mostly when you see that Java is slow, it's mostly because the application itself is slow, or the setup that we added to the Java runtime in AWS Lambda makes it slow. So that's good news, because that means that in ideal world, we can shave off everything from our application that is not necessary, and we can get to similar startup times to other languages. We can get very close to 50 milliseconds, like on this graph. And we can also demonstrate this. With plain Java, I have a small demo that really shows that at least on my computer I can get to these times. If you haven't tried running, or it's been long since you ran a simple application like this, we just print, where is it? Just print something on console, or maybe you never measured how fast it is. You just executed this application from an IDE, which takes some time until it compiles and executes. Here I will show you how long it takes just to support the measurements of this person who did it on AWS Lambda. I won't do it on AWS Lambda this time. I will just show you in the IDE on my computer. Just get us started. So first, the application just outputs hello from plain Java application. But I also have a small script that measures how fast it starts until the end. And here it's 68 milliseconds. I manage sometimes to get to 50. I don't know why. Maybe because of the screen sharing makes my computer a bit slower. So now you can see it's around 100 milliseconds. Normally, when I don't run the screen sharing, then it's around 50 milliseconds, similar to what we saw in the graph. So now the question is, because I want to talk also not only about plain Java, but also about frameworks, whether we can get to frameworks that we usually use to run our Java applications, if we can get close to these Java startup times. And more specifically with Jakarta EE, because Jakarta EE is used by a lot of frameworks and is a technology that we can learn and use with these frameworks without learning everything from scratch. And we can choose a lot of frameworks already. For example, we can choose Quarkus framework, which provides a lot of Jakarta EE specifications, a lot of APIs, provides a lot of other APIs too. And let's see how fast it is with a simple application that does basically the same thing as another application written or run on a traditional Jakarta EE server. Maybe that's what most of you think how fast Java is when you run some application. Running an application server, a lot of people think that application server takes a lot of time to start. So let's measure with a simple application server. This time it's not a full-fledged application server, it's an embedded Glassfish server which doesn't have administration console clustering and things like that, but it supports the whole Jakarta EE specification with all its features, all the API that we can use in our application. And this time I will just run a simple application, simple servlet, which is similar to the Hello World application we had before. It just uses the servlet API and needs the Jakarta EE server to be running. You can see that this is the first web server definition. It processes a request and modifies the response and writes hello from embedded Glassfish to the HTTP response. So let's just have a look and how we run it. We'll first show how it works. How the application looks like before we run a similar application in the cloud in the AWS Lambda. So this is how long it takes. It doesn't take so long, maybe what you would expect with an application server, but still, it takes some time. And let's open page so that you see that it's running. And this is what the application does. It just prints hello from the glassfish. Let's now the application measure. Again, I have a script that measures the application. This time it's not just from the start to the end, because you saw that it's still running all the time. But I will measure from the start until the first request is processed. So it will basically measure how fast can our application start before it's ready to serve first request. You see that there is a response from the request, and from the start to the end it takes 5 seconds. Normally, again, it's faster on my computer, around 2 or 3, around 3 seconds more of the time. But compared to that, let's see what Quarkus can do. Quarkus can do the same thing. I hope I stopped the server. Yes. But in case I don't have any conflicts. And with Quarkus, let's see how the application now behaves or starts. It's the same application, serves a REST endpoint. Where is it? Quarkus. Not Lambda yet, but this one. So with Quarkus, we have very similar. I have it here. We have a very similar application. This time we have only a resource because it uses JAX-RS, which is a different HTTP-related API in Jakarta EE, but it looks very similar. Instead of the API for invoking or processing request and response, there's some mapping, and it means that the hello method is executed when the request comes to this path /hello without any parameters. It just prints hello from SDZ, returns string, and this is converted to the body of the HTTP response. So let's try run it. We see that it started almost immediately, is ready for serving a request. This is what the application gives us. When we access the root, and when we go to hello, we have what we have in our application. For Quarkus, I don't have a script to measure it, so we have to rely on what's on the Quarkus application, or what the Quarkus framework tells us. It says the application is running in 1 second. In reality, it's a bit more because it takes some time for the JVM to initialize, but it should be under 1.5 seconds. What Quarkus is capable to do is it contains an extension for AWS Lambda, which actually includes in the final artifact only what is necessary for running the AWS Lambda. It doesn't include the HTTP stack because we don't have to serve HTTP or server to get the HTTP request. That's what AWS Lambda does for us. It basically just runs our code, provides us the request as an object. So we need to be able to, with our application, we need to be able to just accept this plain Java object, respond to it, and create another Java object which represents the response. Everything else is done by the AWS. I'll switch back to the slides and mention other features of Quarkus, which are also interesting. It does ahead of time code optimization during build, which means that in the time when we build our application, it scans the code, discovers some metadata like annotations in the code, and generates code that will process these annotations during build. So in the end, when in the build application, this metadata is not needed, because the code generated already during build time will do the work. There's no need to scan the annotations, find them when the application is started, but the code generated already knows what to do and how to initialize the application without that. That speeds up things a bit. Another thing is, besides all other things mentioned on this slide, it supports native compilation. Like, native compilation is already supported kind of on Java applications, because you can just take GraalVM Java compiler, take your application and try to compile it into a native library, which means it will now become just a binary which doesn't need a Java virtual machine to start. You can just start it, but it will create a binary for specific systems. So a binary for Linux, binary for Windows, binary for Mac. And when you run it, it's blazingly fast, because it doesn't start Java, it doesn't work with bytecode, everything is compiled to binary code, and it's optimized. It's like a C program. Downside is that it takes a bit more time to compile. And another downside is that not all libraries out there, or even our code, is ready to do this, or ready to be compiled with GraalVM, because GraalVM has some limitations. It can't compile applications using some dynamic features of Java language, like reflection, unless we provide some information how to find this reflection, because it would have to scan a lot of things, and even like guess where we need use reflection, where we need to create new classes. So we need to provide some pointers to the GraalVM compiler to find this code and compile it into the resulting binary. Otherwise, it will ignore the code, ignore the information, and our application, when it's compiled by GraalVM into native binary, it would fail on some occasions when we run it, because the information is not available. And what Quarkus does, where it fits here, it supports native compilation in the way that when you use the Quarkus functionality, Quarkus components themselves, they're ready for GraalVM compilation. But it also supports building extensions that are ready, or that provide these metadata or changes, or even provide data for the build time mechanism to collect information from the codes to generate some code. And anybody can build these extensions. In fact, a lot of standard features in Quarkus are created as extensions, and there are a lot other third-party extensions that you can use. And Quarkus has full support of building extensions that support GraalVM. So, for example, you can have an extension for your favorite library that doesn't support GraalVM, but the Quarkus extension, that will wrap this library and provide support for using it in GraalVM, or compiling it using GraalVM into a binary. And the extensions also can inject into the build time lifecycle, into Quarkus at build time, and generate some code that will be used when you start the application. I can show you some how it works for AWS Lambda, for example. When we look at the Quarkus AWS Lambda project, let's see at the POM XML. With Lambda, we need to use a special dependency, Quarkus Amazon Lambda, which is an extension into Quarkus, besides all other standard Quarkus components. And this one will, during build time, will hook into the build process and change the compilation or change the creation of the application in the end. And I have it here. Quarkus Lambda, function target. Let's have a look at the final artifact. And if we look inside the jar that is generated by this build process, it's not that big as I would like it to have to be. No, not this one. Yes, this one is what I wanted to show you. When we look at the code of our application, Java.org, we have two classes here. One is, this is a different one that I showed you before. This one already uses person entity for mapping the incoming JSON. So this is more complicated. It contains two classes. First one is for Lambda, which is a slightly different to what we had before. Before we had Jaxar as HTTP resource. Now we have Lambda resource, which implements request handler. This is a handler from AWS API, which we have to use so that AWS will call our code. So AWS Lambda will code actually this method, and it will map. Actually, it won't map directly the person input, but Quarkus will do it for us. So Quarkus, in fact, provides the handler for AWS Lambda. So AWS Lambda first calls the Quarkus handler, and this Quarkus handler calls our method and provides some Quarkus syntax or Quarkus features that we can use already in our code. Without that, we would have to handle a request that gets the raw HTTP request, and we would have to convert it. So with this, we have two classes: greetings Lambda person, which is another class. But in the final artifacts here, we can see three classes. And there is greeting Lambda being class, which is not generated by the Java itself. It's not a nested class or anything like that. It's really generated by the Quarkus framework during build time. And this class contains all the initialization that needs to be done by Quarkus based on the rules that it supports. Here, there's not much special, but we could also have injection here, inject person to support dependency injection. And in this case, Quarkus would have to generate, and it would generate code that injects this person when it creates this greeting Lambda class. And this would be added as a new class here into this bean. So this bean would have the code that would know how to inject the person entity here. No longer with traditional Jakarta servers, when you have an application like this, it the injection would happen dynamically, but for that, the application server would need to discover that there is a field being injected during deployment, which actually means during start time of our application, before it's running and ready to serve requests. Server would have to scan our code and then create a mechanism how to inject the code, the instance of person entity. But Quarkus does it in a different way. It pre-generates code that is just executed when we need to create new greetings lambda bean. It's executed and it will initialize the person entity. So that's an example of an optimization that Quarkus does for us to makes it faster to start Java in AWS Lambda, or even without AWS Lambda, because this is supported in any deployment target any way we want to run the Quarkus application. What is specific to AWS Lambda plugin in Quarkus is that it supports the AWS Lambda interfaces, and it generates AWS Lambda handler, which works like a proxy that forwards requests to our lambdas, our lambdas handlers that we wrote. So that's one approach. Another approach is Piranha Clouds, which is a different framework that also supports a lot of Jakarta EE APIs. And it's in fact based on Glassfish, the same Glassfish embedded that we saw earlier in this session, which takes a good few seconds to start. Now the Piranha Cloud is an attempt to redesign how Glassfish works and add some other components. So it's no longer Glassfish itself. It just takes some components there which are reusable. Some of them are already existing separate projects like Jersey, Eclipsing Worlds, and quite well known. Some others are less known, and some others were extracted from Glassfish by the Glassfish team to allow them to reuse in projects like Piranha Clouds. So Piranha Clouds approach is a bit different to Quarkus. It allows us to assemble our application from small pieces, very granular pieces, up to bigger pieces. So we can only choose what we want to do and what our application needs, based on the fast servlet container, which was written from scratch. So that's basically the heart of Piranha Cloud, which is not borrowed or not taken from any other project. It was recreated, and it supports the standard servlet API. What it means is that we don't have to only run servlets, but we can also deploy third-party servlets. Like, for example, when I mentioned Jersey, that implements REST API, is implemented in Piranha Cloud as a Jersey servlet, which is provided by the Jersey project. And the Jersey servlet is deployed on the servlet container in a standard way. So what's needed only as an integration layer to have the servlet container, and Piranha servlet container is very fast, very easy to work with, very easy to deploy other servlets. And it's also very easy to work with the application because you have a flat class path. So you don't have the complicated class path or class loader issues that you often have with, or sometimes have with application servers like Glassfish, because application servers usually have several layers of class loaders to isolate the application code from the server code. With Piranha, everything can be in the same flat class path as we do with normal simple applications. And we don't have to deploy. We can deploy to a Piranha server, which is one of the ways how Piranha applications can work. But we can just run our code from command line with everything bundled together, and the code just runs fast and starts fast. Piranha provides several distributions so that we don't have to start with from the bare bones servlet. We can start with some distribution that provides already some subset of Jakarta EE's functionality. And we only need to add one dependency to our project, and then we can use all of these functionalities provided by the distribution. Like we can use Jakarta EE core profile, which provides REST, dependency injection, JSON supports, and things like that. Especially for REST services, and it's also convenient for AWS Lambda, because that's what we need to do there. We need to process an incoming HTTP request. Not always. Sometimes it's a different type of event. It can also come from a queue or from a database. But very often, if we want to work with or run applications that have a web interface, we process incoming HTTP requests. And the one thing I like to stress is that Quarkus does a lot, but sometimes it appears like a magic because it generates code. In Piranha Clouds, maybe it's not so clever, but it's very convenient to write applications, and it doesn't have any magic. So it's easy to go into the code or go into the documentation, see the results of our application, what the application does, map to what we write in the application, and which component we use from Piranha stack in our application. Yeah, so I jumped to the next slide. I want to show you how it looks like when we work with Piranha and how the application starts, or how fast it starts with Piranha. This time we can, because Piranha is a bit more flexible, although it takes a bit longer to set up everything. It's more flexible because we can choose what we want, and it also means that in the same project, we can easily run a Piranha application on our computer and also create a deployment for AWS Lambda service. Let's see how it looks like. I close these things I don't need. There's Piranha function. First, Piranha function application. It contains a very similar servlet that we saw with Glassfish. Is again the standard that is supported by any Jakarta EE runtime. In this case, we only need the servlet container from Piranha. So we need to create it, because this is how Piranha works. It no longer is everything is generated or added as a dependency on command line. This is more like a library approach where we can create everything by ourselves. Another approach is, which I won't show, is to create the standard web application WAR file and run it with Piranha from command line, and that sort of behaves similarly how we deploy applications to application servers, but it runs very fast because there's no deployment. It's just Piranha is started, and then it takes our code, and our code is added to the servlet container, and that's it. But when we embed, which is very, very useful for AWS functions, we can create our own instance of Piranha in our code, add the servlet. We can configure the servlet container by other API methods. We don't have to do it with WebXML, what we usually do with application servers, and then we start it. But we still don't have everything that we need to run it on the local computer. We have to add one more thing. We have to add HTTP listener, because this only starts the engine. It starts the servlet that processes incoming HTTP Java object and creates a new Java object. For AWS Lambda, it's enough, but for where do I have that option? Piranha up here. But for running it on local computer, we need to add another layer, which is not this one. Sorry, HTTP server. Let me show the code. So here we create the Piranha instance as we did in the previous projects, but we have to add. I just don't have a project that does both, but we could create HTTP web application server processor and an HTTP and this diff HTTP server inside here. Actually, we can do that right now. Let's go to the function. Just don't do that. We create just Piranha object, but in the main method, which would be only started in our local computer, because main method is not started by in AWS Lambda environment. We can, just for the sake of trying on our local computer, we can create this. I probably don't have these dependencies in my project, but once I add them as additional dependencies, as additional library, I will be able to call this main method just to test my Lambda application and create an HTTP server that listens to incoming HTTP request, translates it into an Java object, and then from that point it goes on with it's in the same way as AWS Lambda, which also does the same way. It just produces the API gateway proxy request event, which is a plain Java object that represents an HTTP request that came through via the API gateway. In AWS Lambda, HTTP requests can come from different services. So this is the event generated by the API gateway, and we need to understand it. It's basically just a JSON that is mapped to these objects. So we can also read it in a different way. We can read it as a string and parse it as a JSON. If we use Piranha, we would do something different. We get the object, and we need to translate it into an object that Piranha understands. We do it with an embedded request builder, and with embedded request builder, we create an object for Piranha based on what we get from the AWS object. So in the basic scenario, we just copy the path so that we invoke the server that we want, and that's it. For request, we don't need to have anything because the request is empty. We don't use anything from the request. We just print hello world to the response. So for the response, we need to do the same. We need to create a response object that AWS Lambda understands, and we do it based on the results of the Piranha service call. So it goes like this. We get a Lambda Java object. We translate it to a Java object for Piranha engine. We call the service method, which runs our application. The request is processed. We get the output of the application as a response object from Piranha, and we need to translate it back to what AWS Lambda expects. So we create this response object and copy the data from the response generated by Piranha. The intention in the future is that the Piranha project will provide a wrapper like this, so we don't need to write this wrapper ourselves. But right now, this is a working process, so I can demonstrate it. We have to write this code manually. What I can demonstrate is how this behaves in our local computer and also in AWS Lambda. So I don't have much time, but I think I have enough to just to show you how it works. So when I run the application on the local computer, I can run it very easily as a standard Java application. And the application is running and ready to serve requests. You saw that it's fast. I can also measure how fast it starts and serves the first request. That's around half a second. So in this case, it's very simple application. It's already a bit faster than Quarkus, but on the other hand, Quarkus does a bit more already. It provides dependency injection. For dependency injection, we would need to add something more to this simple application in Piranha, and then it would take about the same time with Quarkus and Piranha when you launch a similar application. But now we can run this same application also in Quarkus or also in Lambda. So let's see. Here we have a function for that. Function up. Yes, this one. Oh, I think I lost. Run a function infrastructure. Here are the instructions. So I will have to skip something that I wanted to show you, especially the CDK Java code that sets up the AWS Lambda, which basically creates the Lambda, tells it to use our custom runtime with Java 17, and we will just run the code that does it. So we just need to run, when we have this ready, we just need to run this code. It takes some time to deploy our application. Meanwhile, let's see how we execute it. We have a script that invokes our application from the command line. So it actually uses my CDK, my AWS credentials to invoke the Lambda and pass it to some JSON request and then shows the response. So we have some payload which is empty because our application ignores it. And there's the script that invokes our application. I'll just run it. Let's it's still deploying. Okay, it took 1 minute to deploy our application to AWS Lambda. Now we launch it. And now we see, I'll try to make it bigger. Now we see that the duration was 1 second, including the cold start. So it's quite nice that we can, with Java, we can build fast applications that start fast and are pretty small. There are some other options that we can use to optimize the startup time in AWS Lambda. There is just a small comparison of them. I did some local management, so it's not really like scientific comparison. But I tried several options, and it turns out that if we use class data sharing, it is an optimization that caches information about classes, and we also use or disable second layer tired compilation, so it stops the just-in-time compiler after the first phase because it's already good enough for our application. We can reduce the startup times even almost to half a second with cold starts, which is again nice. There is also another option to use native binary with Quarkus, which no longer needs Java to start the application, which is even faster. And then there are other options like Crack, which is an alternative to native binary because that doesn't use the binary compilation, but it uses something like or they call it a checkpoint. When we start our application, basically before we deploy it, remember the state of the application, and we can deploy them to AWS Lambda together with the state. And our application, when it started, it basically continues the work that we did before. So we can save the time in AWS Lambda when we start the application and remember what it does every time when we start it. And then we can skip this and continue from that point. And that basically shortens down the startup time almost to zero because everything is remembered, and the JVM will start right when it's ready to serve requests. So that's it. I almost filled my time, but I think there's still time for questions. So if you have any questions, let me know. If you don't have any questions right now, but you have questions later, you can find me either through Omnifish page, the page of my company, or through my page, or just Google me out. I have a Twitter account. I have a Mastodon account. I'm on the internet. I have a blog, which is easy to find on the internet. So contact me by any means, and I'll be happy to answer questions.
Ondro, I'll jump in. Thank you for your amazing presentation. I see you've covered quite a lot of material. I'll certainly rewatch it afterwards. One question or one theme that seems coming back is, are those slides hosted somewhere? Are they going to be hosted somewhere?
Yes, they are, and they will be. So I don't know how I share the link to these slides. Maybe I'll try to do it in the chat. And of course, I think this presentation will be recorded or is recorded. So it will be uploaded at the Jade Champions Conference YouTube channel later. And I'll try to share it by the means I will organize with you and the Jade Champions Conference organizers. But yes, this is already available.
I think YouTube is quite quick in that regard. In that case, thank you very much for taking the time. I'm going to wish you a great day, a great rest of the week, and may the force be with you. Take care. Bye-bye.
Thank you very much, Alex, for moderating my talk, and everybody else for watching. And I hope you learned something new today. And yes, as I said, contact me if you have any further questions. Thank you.
Until next time. Bye-bye.
Bye-bye.